Hello, everybody. It's time to go on to the next topic. And the next topic is one of the most important topics in artificial intelligence today. It's the beginnings of talking about machine learning, deep learning, everything you've been hearing about in the newspapers and all the hype that's been going on. Uh, some of it is true. Machine learning is an amazing way of doing things. Now, what are we talking about? We're talking about creating a program that will learn how to classify things. For example, we would like a program to be a spam detector. If it thinks that the email coming in is spam, it quarantines it and tells us about it. Now, we could spend a lot of time trying to figure out how we should weigh an email based on lots of characteristics. But we don't have to. What we can do is put those characteristics in a program, use a set where we know the answer. It's called the training set. So we have a set of emails. We have the values of whatever characteristics we want, and whether or not we consider that email spam. And then we tell the program to figure out how to set up the weights so that it will get the right answer most of the time. Then once it figures out how to do it, the program can now be given other emails that have characteristics it's never seen, has a set of numbers in the characteristics it's probably never seen before, and tell us whether it thinks it's spam or not. This is quite an amazing thing to do. The program, we start out without knowing what the answer should be. And the program figures out the answers. That's where the machine learning is. Now, this sounds like it might be very complicated. It does have complications, but at heart, it's a fairly simple concept. The problem comes as you get past the first few stages, when you start having to really dig in to some mathematics to train it and to check out the answers and things like that. So let's begin. We're going to try to imitate the human mind. Now, the human mind has lots of neurons in it. Neurons take in inputs from other neurons, and then they produce outputs which they send on to other neurons. The mind is a huge network of these. There are so many that we just can't imitate it at this point with our machines. But we can use the concept and see how close we can get with a smaller set of neurons and maybe less connections. The unit we work with is called a perceptron. It's sort of a neuron, but a little bit, it perceives something. So what do? We have inputs. So in this picture here, I have input 0 and input 1. And I have weights, weight 0 and weight 1. What I'm going to do is I'm going to take input 1 and multiply it by weight 1 and add to it input 2 times weight 2. Then I'm also going to allow myself to add another number, which we'll call a bias. Now, this could lead to some very large numbers or very small numbers, and it wouldn't be reasonable it'd be hard to work with them. So we take the number we're given and we squash it down into a smaller interval without losing anything, because we can always know which numbers go where in this interval. There's a special function that is used often for this, and we'll look at that function. And then the result of that function on the arithmetic we did is the output. Now, for example, there is a test case that I'm going to show you later this week that has over 50 characteristics of emails. And it has many cases where it has values for those 50 characteristics and whether or not it thinks it's spam. It decides if it thinks it's spam by a 1 or a 0. 1 might represent spam, 0 might represent not spam. I don't remember which direction it goes. All the inputs are numeric. They've been translated into some kind of numeric code so that we can work with them. Some of these characteristics are, for example, how often certain words are used, how many capital letters scream at you consecutively. These are characteristics that people think might determine the difference between spam and not spam. The computer is going to look at this, try to figure out which ones are more important than other ones, how it should add the traits together, and try to produce the same answers we get. This particular set will be a training set. We know the answers. We just want the machine to try to find the answers by its own finagling of the weights and the biases. Now, the more formal way to look at this is that the normalizing function is f, and what we're feeding into f is I0, the input, times its weight 0, plus I2 times its weight, I1 times its weight, plus the bias, where f is the function that we want to use. A function that is used a fair amount of the time is called the sigmoid function. What it is 1 over 1 plus e to the minus t, where t is the input. Now, the reason it's good is it gives us values between 0 and 1. So it squashes things down for us. If we represent the inputs as matrices, so the matrix of the inputs is all the inputs. Here I've made it a one row by however many inputs we have. And the weights are a matrix, and I've made it one column by as many inputs as we have. Then the mathematics of linear algebra defines a dot product to be L0 times W0 plus L1 times W1. Now, the rule for a dot product is they're supposed to line up properly. The number of rows in the first one should be the same as the number of columns in the, the number of, there are 2 rows, it's a 1 by 2 and a 2 by 1. The middle 2 numbers are supposed to be the same. However, our programs don't care, or the program I'm going to show you doesn't care anyway, at least in this simple case. Now, I picked up a Python program that does this. It uses a package called NumPy, which is one of the best packages around for doing a lot of data analysis, the whole idea of data science. Python is the language of choice for this. There are one or two others. R is another language that's used, but Python is the language these days, and it's known to be much simpler than the other languages we use. So, despite the fact that you might not know Python, I think you'll be able to follow along when you look at these programs. Why NP? NP allows us to create arrays very easily. It also has the dot product in it as well as other such things. And it has some arithmetic capabilities. It can take e to a power, which is what we need to compute the sigmoid. So it has all the things we want. So let's look at the program. We started out with W0 equals 0, W1 equal 1, and the bias equal 4, and we're going to use the sigmoid function as the normalizer. So here's the program. First, we have to import numpy, and since we don't want to type numpy all the time, we put np as a substitute for it, a shortcut. We define a function, sigmoid of x. What does it do? It returns 1 divided by 1 plus np.exponent. That's how we get to the exponent that's part of the np package, minus the input we give it. Now we define a class. Many of you might not have gotten to classes when you did Python. I know when I taught it last time, I didn't get that far, but it's going to be taught in 103 from now on because it is necessary. A class is just like a class in other languages. It gives us a set of methods, a set of variables that are in the class. The one interesting thing about it is this variable self. Technically, every method has self as its first argument, but we never write it because it sort of appears on the other side of the method. But the self in these items refers to the object of this class, whatever we've declared as in this case, neuron is an object, and we refer to that object as self when we want to do it. There's a similar concept in C++ called this, THIS, which allows you to refer to the object that you have attached to this method, or that you've attached this method to. So the arithmetic is very straightforward. It takes in the values, produces the dot product, adds in the self-bias, and returns the sigmoid of it. And we get to use it, we create an array of weights, 0 and 1. We create a bias. We create a neuron given those weights and bias. If you'll notice up here, the initialization sigma of neuron, the init, there's an init in this language. There's a similar thing in C++ called the constructor. This is the constructor, and it sets up these items. And then once we get that, we call the function and we get the answer. And this is a particular case. This is the case 2 and 3 as inputs. You could change those inputs and see what happens. Now that's a very low-level first look at it. Networks are more complicated than that, the learning machines. They have hidden layers. They have more layers in between the input and the output. That way we can play around with different combinations of the input. Otherwise, we'd be very limited. So here's a simple one, probably too simple. We just take the inputs and send them to two hidden layers, and then the hidden layers work to send them to the output. Now, a hidden layer contains the same perceptron types that are in the input layer. So it uses the weights and it uses the bias. In our examples here, it uses the same weights and the same bias, I believe. Now, I have found the code from the exact same website I gave you the code before to implement this network. It has to have the code we had before, and then it defines a special network here, a new class, on neural network, and it initializes it. It has the weights again. It starts, this time it's going to have weights 0 and 1 and a bias of 0. And it also creates two neurons on the hidden layer and one neuron as the output. So they are defined as neurons. They're created as neurons. The concept that we're working with is called feed forward. Feed forward means that we take the outputs of one layer and feed them forward to the next layer. That's all it means. So let's look at what we get. Out H1 should be whatever H1 gets from feed forward with X. Now that's a recursive call. So that says H1 is to perform the arithmetic on its inputs. And its inputs are whatever we're passing in to the feed forward function. So they're the inputs that will be I0 and I1. This section produces H1 and H2's outputs and then returns the out based on these two. Remember, out is defined here, and it's a neuron, so it takes the input from these two hidden neurons and does the same work that was done in the other. That's what's returned. This is our input, 2 and 3. We send it into network, which is the neural network we created, and we ask it to do a feed forward to get us the answer for this particular case. Now, up to now, we've used, I think, minimal mathematics. You may not think so, but I think so. We've used the dot product and matrices. That's from linear algebra. It's one of the easier parts of linear algebra. And I will tell you that it seems that NP doesn't make a big distinction about row or column vectors, or row, the matrices I have. It may when we get to higher dimensions, but right now it doesn't seem to have a problem with it. The problem now is, this was an example I'm going to do. I mentioned it a minute ago, determining if emails are spam. The problem that we have is that we've only done a small part of it. What we have to do is we have to train the program to determine what weights and biases it should use. We do that by having a group of cases, of emails, where we have the characteristics they have, whatever the inputs would be, and we know whether they're spam or not spam. So this is a set of known cases. We feed it to the learning program, and the learning program computes what it thinks the answers are. Then it takes the answers it computes versus the correct answers, and it has to determine how well it did. In other words, it has to grade itself on what it did. So we need to figure out some way to determine how we grade the answer. Next, if we don't like how well it did, if it got an F minus or something like that, then we need to vary the weights and biases to see if we can get a better result. And how do we do that? We actually use partial derivatives to figure that out. It's called the gradient method. And what the machine does is it keeps iterating and iterating on the set of known cases until it likes the answer or until it gives up. Now, here's the algorithm in a very general form. Input a set of examples. But for each example, you know the characteristics of the email and odd determination if the email is spam or not. Input initial weights and biases. They can be as simple as 0, 1, and 0 if you want to. Repeat the following steps. Compute the output for each case. Now, we'll determine if it's spam or not spam. We'll use two values, 0 and 1. 0 might be spam, 1 might be spam. The other one is the not spam. Figure out how good it did. This is the grading I was talking about before. One of the suggested methods is one that you may have seen before if you've taken any probability and statistics courses. It's taking the expected answers, the answers we think are correct, and the computed answers, the answer the machine begins. And in each case, we form the difference of those two, square it, then we add all the squares together and divide by how many cases there are. That's called the mean squared difference. And it's a fairly common method because it's relatively easy to compute and it works. If the measure is acceptable, we're done. If the measure is not acceptable, we use the partial derivatives to compute some numbers which we're going to use to change the weights and biases. We change the weights and biases, but we also have to incorporate another parameter, that is how fast we want the program to move forward or not. Sometimes if you go too fast, you miss the best possibility. So you have to play around with this. You have to see what works best. How big a change should you make each time, depending on what number was computed. Should you multiply it by 2? Should you multiply it by 1/2 before you make the change? And we can keep doing this essentially forever because we get out of it by the breakup here. So I'm thinking of this as a while loop. And if we do that, when we finish, we have a program to determine if an email is spam. And I think the most amazing part of this is that we don't know the weights or biases that are being used. We could look, but we didn't figure them out. All we did was decide on what characteristics we wanted the machine to consider. And the machine may have considered that some of these characteristics are so poor that it put a weight of 0 on them, for all we know. But we put in what we think was significant, and then instead of having to figure out how we should go about taking care of the weights of each of these and putting that all together, we let the machine do that. Now, I don't know if you're too jaded to think about this as something amazing. Basically, the computer is determining how to interpret the various characteristics we give it. We have done very little of the work. We've let the computer do the learning. So that's where I'm going to go now. The next the thing I will do, and I'll probably put together a video for tomorrow or for Monday, is to talk about the two sections up here that I haven't done yet. Computing the measure and using the partial derivatives. It is not trivial. I tried some this summer when I was looking over this to make sure that I knew what machine learning was. And it can be complicated. But I think we can write some relatively simple ones to give you the feeling for what is happening. So that's it for now. Have a nice rest of the weekend, and realize we're getting towards the end. We're moving through the semester pretty fast. So long now.